continue on with our sort of introduction to all things hashing, looking at balanced allocations, cuckoo hashing, and related stuff. So again, the sort of thematic focus here is looking at the issue of the power of multiple choices, right? So typically when we think of hashing, and I'll often refer to hashing as sort of balls and bins type setting. Normally when we think of hashing, we think of having a single hash function. You throw a ball randomly into one of the bins, and then you might look at things like the load distribution of the bins. But one of the things we started to see with Bloom filters and so on is you can get power from multiple choices. And here we're going to look at power of multiple choices in a different way, or a different sort of setting. Right, so here you can imagine building up a hash table where you're storing items, but you give each item a few choices, right? So each item is going to have D associated hash functions, and we can think of this as getting sort of D choices uniformly at random. And in order to get a distribution on the load table that's as sort of even as possible, right, the natural thing you might do is you say, well, given these choices, I'm going to end up placing it into the least loaded, right, as denoted here by the solid arrow. And the question is, what does this buy you? Does this gain you anything? And sort of the seminal version of this result by Azar, Roeder, Carlin, Upwall, dating back a ways now, is that if we throw n balls into n bins using this type of approach, that the maximum load normally, if we just have one choice, is going to be something like log n over log n. That's not actually due to them, that was known well beforehand. But now if you're going to place n balls into n bins and each gets d choices, the maximum load is now going to go like log n over log d. In particular, just going from one choice to two choice gives you a completely different type of behavior, right? Going from one choice to two choice gives you a log n as opposed to essentially a log n type of behavior. Going from two choices to three choices or four choices, that still improves things, but unfortunately it doesn't turn it into like log or log. It just changes the constant factor. But what we find is that you get this sort of log improvement. And it turns out that can actually be very substantial in a lot of situations. And I'll have some numbers coming up soon. Okay, so again, you can view this in another way. You could just view this as having a split table and getting one choice from each of the D subtables. And again, that really doesn't affect anything, although it can, as we'll talk about in just a sec. Okay, and the point of this is, you can think of this in terms of trade-offs. You can significantly reduce the load, but now you have to check D locations. Again, if we think of this as being a sort of split hash table, which is maybe more natural in a hardware type setting, right, then you can make those D choices parallelizable, right? So you're not necessarily paying a time cost for having to access those D locations, as long as you can do them in parallel, but it might come with some other associated costs, right? So if we're thinking in terms of hardware, for example, having to check those D locations, you can do it in parallel, but now you might have a greater pin count, right? You need to be able to access these sort of D different sub areas of memory all at the same time. And now you can start thinking of combining these sorts of ideas. Well, if I've got D choices of where to look, and I wanted to not actually take that expensive step of going to memory, going to these D possible locations in memory, but I wanted to somehow, only look at one of the memories, or with high probability check only one of the memories, you can imagine using things like Bloom filters to tell you which of the memories do I have to look at. Right? You could have that be sort of an on-chip, like pre-processing stage. Right? Which of these locations do I have to look at? and a false positive here might send you to look at some portion of the memory that you actually don't need to look at. All right, so this can be very useful, this sort of technique, when you want to sort of get a highly packed hash table where you're really concerned about memory. And in particular, you might want to have your buckets, right, correspond to a cache line. And you really don't want there to be overflow. You want the maximum load to be very small and tightly concentrated. And this is exactly the sort of situation where using multiple choices can help you. So this is used in a lot of networking type applications, hash tables for routers, or other networking systems, where you really have to limit the number of things that you can stick into any particular cache line, into any particular bucket. And the point is that if you just use one choice, the maximum load is itself, besides being large, is also, it turns out, going to be highly variable, significantly variable, whereas when you're using multiple choices, another sort of thing that you get out of the gain is not only is it a much smaller, higher load, but it tends to be very tightly concentrated. So how do we analyze these sorts of schemes? Okay, well, there are actually multiple methods in the literature for looking at these sorts of schemes. There's sort of what I call a layered induction approach, where you sort of inductively bound the fraction of bins with load at least 1, at least 2, at least 3, and so on. There are things called witness tree arguments, where you sort of say that a bad event corresponds to something with the load being too high, and you build this sort of structure, turns out to look like a tree in most cases, where the structure implies that you have a bin of a significantly high load, and then you bound the probability of a witness tree. Or another method that turns out to be quite useful numerically is based on fluid limits. And most of my work has been on this third type of fluid limits, and so I'm going to sort of present that because I think it gives some good intuition. But if you look at, for instance, I have a survey on two-choice schemes that uses these sorts of things, or I'll put up at some point on for the website sort of a list of references for some of these other sorts of techniques or other types of methods of analysis. But for right now, let me try to explain how the fluid limits approach tends to work. All right, so let's suppose right now that we were looking at this two-choice system and throwing, say, n balls into n bins. We want to start with just an easy question. Forget the load distribution. Let's just try and figure out what fraction of the bins end up being empty. Right? So if we were just doing one choice, this is an easy question. Right? We just figure out what's the probability that a single bin is missed. Right? That would be 1 minus 1 over n to the nth power, or 1 over e fraction. Turn out to be missed, and then we can say things about it being closely tied around its expectation if we want to, but it's easy to figure out the probability a single bin is missed. When we have multiple choices, it's a bit harder, right? Because it's not just whether something's missed or not, it's whether a ball actually gets placed there. All right, so the way to do this is we're going to think of time as being scaled. So we're going to think of the n balls as being thrown in 1 second. So we'll think of like our delta in time for each of the balls as being 1 over n. And if we let x of t be the fraction of the non-empty bins, let's think of what happens to that fraction over time. Okay? So here I'm talking about the expected delta xt, right? So the expected change in xt over one time step. Okay, that's what the delta xt refers to. The change in xt over one time step. Well, when is xt going to change? When is the fraction of non-empty bins going to change? It's when a ball gets put into an empty bin. Okay. When will a ball get put into an empty bin? It will get put into an empty bin as long as all of my choices, or at least one of my choices, is empty. fraction of non-empty bins, what's the probability that that I have at least one choice that's not empty? Well, the probability that all of my choices are non-empty is xt to the bth power. So the probability that there's at least one that's not empty is 1 minus that. And then again, since I'm talking about the expected change in the fraction of non-empty bins, I have to divide that by n. So is this top equation more or less clear to people? Are there any questions on that? All right, now the point is that here I'm talking about delta xt, the change in over a time step, where my time steps are 1 over n. Now if we think of n as growing large and looking at the limit of this, right, then this becomes, this expected change in delta xt can become a dx. And the change in time is going to be a small change in time dt. And we can look at this as a sort of as the continuous version, which is a differential equation. dx dt is 1 minus x to the bth power. Note that the n's just cancel out when I do this division. All right, so what I want to say, or what I'm going to ask you to believe for the moment, is that the limiting behavior of this system, right, is adequately described by this differential equation. As n goes to infinity, the behavior of the system, assuming things behave close to their expectation, is just going to be given by this differential equation. So this is a nice, pleasant differential equation. It doesn't generally have a pleasant closed form solution, but it's certainly very easy to calculate the given values. So if I'm throwing n balls into n bins, I have to figure out what happens at t equals 1, given that x naught is 0, and I can figure out what x1 is. Right? Or x1 for d equals 2, I can figure it out for other values as well. So what this is saying is that the fraction of non-empty bins is going to be about 76%. And if you do simulations, you'll find that this matches. All right, so that's good if all I care about is the non-empty bins. What about if I want to generalize to actually figuring out the loads? All right, so let me have this notation. Instead of x's, I'll use sk of t to be the fractions of bins with load at least k. And again, it's going to be, it turns out it's nicer with these equations to look at what I'll call the tails, right? To look at the bins with load at least k as opposed to exactly k. Obviously, if we've got the tails, we can figure out the loads with exactly k from these values with load at least k. But it's going to be easier to write equations in terms of these variables. Right? So in particular, here I have, again, the same sort of equations, and let's look at where this equation comes from. Okay? So I claim that the expected change in sk of t, okay, it starts out as being sk minus 1 of t to the d power. What this value represents is this is the probability that all my d choices have load at least k minus 1. Because if sk is going to increase, when is sk going to increase? It's going to increase when my least loaded bin has load k minus 1. So in particular, I can't have any load smaller than k minus 1, so I certainly need all my d choices to have load at least k minus 1. On the other hand, this is overcounting what I need slightly, because if all my bins have load at least k, right, then I'm not going to increase the number of bins with load at least k. I want to have it that at least one of my bins has load exactly k minus 1. And that's given exactly by this expression. All my bins should have load at least k minus 1, but they shouldn't all have load at least k. So this sort of pleasant form is sort of what justifies looking at the tails. And so now I have a family of differential equations, dsk dt equals sk And one of the things you should notice about this, and by the way, I should think of, again, S0 of t, the fraction of bins with load at least 0, is obviously going to be 1 throughout, right? That's just going to be, everything's going to have load at least 0. So the point is that I can successively solve these equations, right? I can solve ds1 dt, because that's going to have this value be 1 minus s1 to the d power. Once I've solved for s1, I can solve ds2 dt, because I know what the function s1 is, and so on. Right? I can actually solve these functions successively to find the limits. And now, again, assuming that these differential equations work, I'm going to show to you why, at least intuitively, they justify this log-log n behavior.
Okay. You said that there are no closed form solutions for these differential equations?
Not that I know of,
Even for d equals 2?
For d equals 2, there is for s0, but not for s1, s2, and so on.
S0 is 1.
Oh, sorry, s1. Sorry. For s1, you can. So, and I think if for d equals 3, there's a closed form specifically for s1, but you can't get closed forms for all these values. All right, so I'm going to use this to justify a sort of double exponential decrease, right? So we have that dsk dt is sk minus 1 to the d power minus sk to the d power. So in particular, dsk dt, let's just get rid of this sort of hopefully smaller, lower order term, this sk to the d. dsk dt is certainly less than sk minus 1 to the d power, okay, at the appropriate time value t. And in particular, these sk values are just increasing, right? The fractions have been with load at least whatever is just going up as time goes on. So this is less than or equal to sk1, sk minus 1 of 1 to the d power. Okay, so the way to think of this, what this is telling you is that the rate that sk is increasing over time is less than or equal to always sort of the n fraction of the fraction of bins with load at least k minus 1 raised to the d power. So what does that mean? Well, sk of 1, right, if I sort of integrate this expression from 0 to 1, right, think of putting a little integral from 0 to 1 here, and then you'll go from 0 to 1 here. Well, if I integrate from 0 to 1, I'm going to get sk of 1. And on this side, I'm going to get that that's less than sk minus 1 of 1 to the d power. And now, just inductively, that means it's less than or equal to sk minus 2 to the d squared power, and so on. It's less than or equal to s1 to the d to the k minus 1 power. Now, s1, whatever it is just some fixed number. It was the fraction of things with load at least 1. And now we're raising it to the d to the k minus first power. Okay. So notice that what this means is that if I choose k to be about log n over log d, plus maybe a constant term, this expression, right, the d to the k here is going to be something like order log n, right? And this s1 to the order log n will be less than or equal to 1 over n. And so that means that the fraction of bins at time 1 with load at least k will drop below 1 over n. That is, the fraction of bins is going to be 0. So what this tells you is that the maximum load has to be log n over log d. Because that's the point where this value is going to drop to less than 1 over n, essentially fall to 0. All right, now, to formalize this, we need a couple of things. First, we need that the differential equations are correct. But then, really, there get to be other issues that come in the tail. The way I like to think of this is this gives you sort of intuition to do what I was calling before a layered induction. Right? This is telling you sort of inductively that the fraction of bins with load at least k at time 1 is sort of is about the dth power of a fraction of k minus 1. So if you can prove something like that inductively, that's what will give you this log n over log of t down. Okay, now, what justifies this sort of approach? It's actually, this dates back some number of decades, some work by Kurtz. If you've seen this sort of thing before, you may also know it as some work by Nicholas Wormold, who did some later work on this too, getting similar sorts of results. But basically what it tells you is that if we look at this sort of limiting approach, if we look over finite time intervals and for fixed dimensions, the deviation of the random process from the differential equations, you're going to get this sort of tight concentration. You're going to get Chernoff-like bounds. Right? So your random process is going to behave very close to the differential equations with high probability. Now again, this is for fixed time intervals, which we have. Right? We were running till time 1 for n balls into n bins. If we were doing like 2 n balls into n bins, that just would have meant running to time 2. That would have been fine. But it gets to be a bit problematic since we're going to look at loads of up to log n. That's not fixed finite dimensional. Right? As n goes to infinity, log n still goes to infinity. Right? So these differential equations essentially work up for any constant load, but you have to do a bit of extra fussing to get things up to that log n bound and turn it into a layered induction. But still, it gives you sort of the right numbers. And I'm not sure I have any slides in here that show this, but one of the amazing things is like when you produce these numbers, when you solve the differential equations, and then do simulations, you really get out exactly what the differential equations tell you. So unlike a lot of theoretical approaches, right, which will give you order bounds, like it's order log n, right, or log n plus order 1, and you can't really tell what the order 1 is. This approach, this fluid limit approach, will really give you sort of the exact behavior, and when you actually run these sorts of experiments, you will see the behavior predicted by the differential equations with very small deviations. And that's one of the, I think, powers of this approach that turn out to make it useful for people who are thinking of building practical systems. Okay, so once you have this basic power of 2, there are oodles and oodles of other possibilities and generalizations, and I'll talk about a small number of them here, but you can come up with all sorts of different ways of varying the problem. Asymmetric load balancing, I'll talk about it in a few seconds. More balls than bins, again, fluid limits works for, if I'm throwing 2 n balls into n bins or 3 n balls, but you might say, what if I have like, n cubed balls into n bins? What happens then? Weighted balls, right now I've been assuming that all of my, if you're thinking in terms of hash tables and load, that's one thing. If you're thinking in terms of load balancing and jobs, your jobs might have different weights, right? So what happens to you if you have weighted balls? What happens if you start out with a sort of unbalanced initial conditions? How long does it take to catch up? I haven't even talked about deletions yet. You might say, what happens if I start deleting things from a hash table? What are the models then? Non-uniform choices. There are all sorts of variations. Let me talk about some of my favorite. One is what we call a supermarket model. So this is more of a load balancing version, where this model is taken from queuing theory. Okay, so we think of arrivals as coming in as a Poisson process. So that just means that the arrival times for arrivals are exponentially distributed. Okay? So many of you may not have actually seen queuing theory. It's something that, strangely, a lot of CS people avoid. But you used to think of it as they're coming in at a rate of lambda times n for lambda is less than 1, and it's not deterministic, but there's sort of an exponential gap in the times. Okay, but we expect lambda n customers essentially to come in per unit time. And I have n servers here, and the mean service time is 1, and also exponentially distributed. So So as long as lambda is less than 1, I should have enough servers to handle the load, modulo the fact that I have to figure out how to distribute them, as evenly as possible. So you could have just each customer going to a random queue. What happens if each customer comes in, chooses, say, 2 random queues and goes to the shortest? This is meant to be an intermediary between sort of a pure random selection and, say, going to the shortest, right? You could imagine it seems like a very good policy, go to the shortest queue. The problem is that that often takes a lot of infrastructure, or could it take time itself to figure out which is the shortest in a big system, whereas just choosing a small number randomly may be very effective. All right, so similar to what we were doing before, we can imagine keeping track of the system over time, where sk of t is going to be the fraction of queues with at least k customers. So now, what's the rate at which customers disappear? Right, so the fraction of queues with k customers is sk minus sk plus 1, because we're dealing with tails. And customers from queues with k customers are going to leave at a rate of, essentially 1 per unit time, right? So it's this fraction times 1 per unit time is the amount leaving. And again, the same sort of expression, what's the probability that someone comes in and then picks something that's going to give me a new queue with load k? They have to have all their d choices have load at least k minus 1, but not all have load at least k. So if I think of this system in equilibrium, right, over a small period of time, right, my arrival rate is lambda n. So over a small period of time, dt, the probability that I get an arrival is going to be lambda n dt. And then the probability it's going to pick a queue with, or give me a queue that will have k customers is sk minus 1 squared minus sk squared over n. And similarly, the rate at which sk decreases is going to be sk minus sk plus 1 times n times this dt over n. Right, that's just the rate at which they're disappearing over a small interval of time. Right, so this gives me, sort of by differential equations, describing what's going on with sk. Here I have, this is the rate of arrivals minus the rate of departures. And now the key is that what I want to have happen in a well-behaved system, right, is that this should converge to some sort of fixed point. Right, this process is going to run forever, but if it's a well-behaved system, it'll converge to a fixed point where these rates go to 0. Right, the changes go to 0. The fraction stays steady. And if you look at the fixed point, right, it turns out that these equations, if you set them equal to 0, they have this nice balance where it will be 0 as long as lambda of sk minus 1 squared is equal to sk, right? Because then also lambda of sk squared here will equal lambda of sk plus 1, right? So it turns out as long as I can get this term to equal this term, and similarly, the lambda times the sk squared term to equal the lambda times the sk plus 1 term, inductively, as long as I have sk as lambda of sk minus 1 squared, each of these expressions is going to be 0. So that gives me inductively that at the fixed point, the tails decrease doubly exponentially. Pi k is going to be lambda of 2 to the k minus 1 first power. So this turns out to be the same sort of power. The difference in going from log n to log n occurs in this queuing setting. If I have one choice, things fall exponentially. The probability of going to a queue of size k falls like lambda to the k. When things have two choices, falls doubly exponentially. And if I had d choices, it would be lambda of d to the k minus 1. So this gives me huge gains, particularly under high loads. Okay. So here's an example of the sorts of simulations versus predictions. This is sort of one choice, and you can see it's already getting, the expected time in the system is growing, and it actually grows, very sharply as you approach 1. At 0.9, it's way off the charts. It's up to 10 already. And if I look at 2 choices, you can see that the double exponential fall off in the tails means my expected time in the system is much, much smaller. Right, again, at 0.9, it was going to be something like 10, and with 2 choices, with 1 choice, and with 2 choices, it's just a little over 2. And 3 choices, as you expect, can help some, but not as much as the big jump from 1 to 2. So some other issues. We talked yesterday about Bloom filters with double hashing, and I said it didn't end up making a difference. That it didn't matter whether you use double hashing or regular hashing for Bloom filters. It turns out the same thing happens with balanced allocations, and this is something just recently proved. And there are different ways you could talk about having the same performance. There are different sorts of results that you could have. Right, so one way of thinking about it is that double hashing, right? Let's recall our model or variation of double hashing, right? Was that we start with 2 hash functions, and then we generate more possible hash values by taking sort of the linear combinations of them. Okay. All right, so one sort of result that you can get is that, well, double hashing already starts with 2 random choices. Okay? And if I start with double hashing and expand it to give me more than 2 random choices, if it gives me d random choices, well, I've at least started with those 2 random choices, and more choices should only make the system work better. So you need to formalize that intuition that more choices really does only make things better. But that immediately gives you that double hashing has already got to be better than having at least 2 random choices, and 2 random choices was already enough to get this sort of double exponential decrease. So certainly double hashing should preserve this double exponential decrease. Using the other method that we talked about before, witness trees, turns out you can go back into the witness tree argument, plug in double hashing, and get pretty close to the same result you got in the original. And that's a fairly technical approach, but at least gives you the right log n over log d at high order term. Right? Method 1 just tells you that it falls like log n over log 2. Going to witness trees will get you that it really falls like log n over log d, so you even get the right constant factor. And then finally, the method 3 is to go back to the fluid limits that we just talked about, these differential equations. And then what you want to show is that it turns out the same differential equations really govern the behavior even when you have double hashing. Okay, and that's not at all clear or obvious. It takes some work to show that. But once you have that you can put things into the same differential equations framework, you can say, well, whether you have random choices or just double hashing choices, you get the same differential equations, so you're going to get the same performance. And here, again, it's not just the same performance in some asymptotic terms, but the same performance in that the fraction of bins with load 1, 2, 3, and so on are going to look the same under both approaches. Okay, so another variation I want to talk about is sometimes called always go left, or I like to call it the be left scheme. This scheme was developed or shown by Bertold Wilking, who I don't know, I know some of you may have known or have heard of, but some of you haven't. He recently passed away. It was a great loss for all of us in computer science. I admit, just because of my love of these sorts of problems, this is probably my favorite work of his, but he has a great number of amazing pieces of work. And so I highly recommend that everyone should, you know, look at his body of work to see some of the amazing things he's done. Looking at this model that he developed, or this result that he came up with, which, you know, sort of when I saw it, sort of knocked me out of my seat. I couldn't believe it, and I had to go run a bunch of simulations before I could believe it. And then after I finally got myself to believe it, it took me days to figure out why it actually worked or how he came up with it. Right? Because this is the approach, he says. Okay, so we're going to work with our sort of split version of the table. Okay. And I should point out that, you know, using a split version of the table, as I said, that in itself doesn't change anything. Right? That would give you the same whether you split or not in terms of the choices. But he added the following idea. Not only are we going to split the table, okay, but, you know, we're always going to put things in the least loaded. But there's this question of what to do when there's a tie. And normally when we think of having D choices and we put things in the least loaded, if there's a tie, we would just say, well, you know, pick one randomly. Right? Or, you know, you could break the ties in any sort of arbitrary fashion when you're just using a single hash table, and it wouldn't matter. But he says, look, if we're using a split hash table, let's actually break ties by placing things to the left. Okay, so if we think of our hash tables being laid out from left to right, if there's a tie, as is the case here, we're always going to break the tie by going to the leftmost choice. Okay, so you need to combine these two ideas. You need a split hash table, and you need this tie-breaking mechanism. So what he was able to show is that this actually does better, right? So remember that we had D left is, or the D random, the maximum load is log n over log D with D choices. D left is log n over, well, there's really a constant here times the D, but you know, here the main point is that it's log n over something that doesn't depend on log D, but depends on D. Okay, so our constant factor has improved significantly by using it in ways that can actually make a difference. And again, I was just shocked to see this. He did this by sort of the witness tree argument. Later, I went back with him and we sort of showed that you could come up with, again, the sort of fluid limit differential equation-based analysis that gave the same sort of result. And just to give an idea of why this is without going through the full proof. So for the D random scheme, remember what we ended up showing is that the fraction of bins with load at least k fell like this, 2 to the minus d to the kth power. And what he was able to show is something even more powerful, that for the D left scheme, the fraction of load with at least k falls like 2 to this constant term, phi of d, but now the d gets up in the second level of the exponent to the d kth power, where here phi of d is the rate of growth of the generalized Fibonacci numbers. So somehow the Fibonacci numbers are coming into play when you do the splitting. And again, I'm not going to go over particularly why the Fibonacci numbers come up. That's takes some understanding, and I don't think is at all intuitive. But I just, also was a big fan of Fibonacci numbers. I'm just amazed that somehow the Fibonacci numbers came into play in this process where it doesn't look like they should appear at all.
What are the generalized Fibonacci numbers?
So Fibonacci numbers, right, are, so these are our normal Fibonacci numbers, right, and the rate of growth of the Fibonacci number, exponent is phi2, right, so that Fn as n gets big is about phi2 to the nth power. Right. So like the The generalized Fibonacci numbers of degree 3 use just adding up the last 3 numbers. And so this system grows approximately like 3 to the n, which is a bit bigger. But these values, the rate of growth is always less than 2 as you get big. Good. Any other questions? All right, so again, I want to give some idea of the tightness of these sorts of things. Right, so if we're using 4 choices, so 4 left, and we set up our table so that the average load was 6. So I was throwing 6 n balls into n bins. The average load was 6. And look at the fraction of bins with load at least each of these values. You can see that, oh yeah, as you might expect, I'm going to see things with load 7, but I'll almost never see things with load 8, and I'll certainly never in the real world see anything with load at least 9. Right? So I could guarantee that if I was trying to throw 6 n balls into n bins, that as long as I made the capacity 8, right, I should be totally fine. Right, so that's like essentially a 75% load, right, throwing 6 n things but needing 8 n slots. And arguably, maybe most of the time I can get away with 7 n slots. I'm almost never going to see things of load 8. Things behave a bit differently when you alternate insertions and deletions. You can actually calculate out that load distribution too, again, using the differential equation approach. But again, even in that case, you might see some things with load 8, but you'll almost never see things with load 9. So this is what I was getting at before when I said that these sorts of D-random or D-left systems, they're very tightly concentrated around their mean. They drop off very quickly after their mean. So I think that's all I'm going to talk about with balanced allocations. Are there any questions before I go on to sort of the next part?
Do you have sort of similar numbers for D-random?
Yeah. So D-random is, again, I can find the slide for you. D-random's a bit worse. Right? D-left's a bit better. Probably for D-random here, you'd actually see things with load 8, and maybe even with load 9, but by the time you got to load 10. But it does mean that D-left is, it's better by 1 or 2, but when you're talking about, if you're talking about building a hash table and having to fit things into a cache line, that corresponds to a non-trivial percentage in terms of your load capacity.
Can you get any rigorous guarantees using the fluid approach?
Yes. So in particular, you can get guarantees about the fractions of load 0 and 1 and 2 and 3 and so on. It's just really up to any constances, technically. Right. All you can deal with.
So you mentioned that there was this result that only holds in fixed dimension. Do you have extensions to that?
I would love to see one. I don't know how it extends to beyond fixed dimensions, at least in the way that computer scientists use that, right? Like I'd like to say, oh, it works up to log n dimensions. But you're taking limits as n goes to infinity, so it's not clear even what that means necessarily at certain points in the proof. You'd have to do some very odd interchanges of limits, which may be problem specific and may not hold in general. I think it's a great, I brought it up with people who do this sort of stuff. I think it's a great open question to say, can you prove a version of this under whatever sorts of conditions that would let me just plug it in and say, yes, I get what I want for log n?
there any lower bound on the minimum, on the maximum load for any D mechanism?
I couldn't hear you.
Is there any lower bound for the
Yes,
maximum
so
load?
I should point out that, I tend to talk about upper bounds, but all of these things sort of have matching lower bounds, right? So it's there is a lower bound using this approach, right, of log n over log d minus O of 1, or minus a lower order term, and same thing with d left as well. So these are all tight, at least in terms of analyzing these algorithms. Generally, the way that works is you sort of, get a bound on the distribution after half the process, and then over the next half of the process, and the next half of the remaining process, and so on. Is one typical way to do that. Okay, good. Any other questions?
Just wondering, all of this is for totally random functions, right?
Yeah.
And sometimes there exists functions in the real world that satisfy this.
Yeah, so for balanced allocations in particular, right, I don't, there's not a lot I can say about practical hash functions necessarily, without making some assumptions about the input. Generally for these things, using the witness tree approach, you can get that order at log n wise independence is sufficient to make these go through. Right, that using the witness trees, you can sort of get that the load at any bin really only depends upon, the maximum load is log n, but sort of there's a history of things colliding or interacting, but the witness tree tells you that those histories are going to be of size order log n. Right, so the order log n independence suffices for the d left to d random results. But saying anything better than order log independence suffices, I don't think is known. Other questions? Okay. All right, so now I'm going to talk about sort of a different way of using multiple choices. You can think of this as an extension of the multiple choice hashing approach I just talked about, except in the multiple choice hashing approaches I was talking about, the idea was like balls were coming in sequentially and they were placed, and once I placed them, that was it. You were done. Right? That ball was not moving again. Right? I had found its place and I wasn't moving it. But in many situations, that isn't a restriction. Right? Maybe I could, I need it to be in one of its two choices, because I'm going to look, when I look it up, I'm going to look at one of those two choices to try and find it. But there's no reason I can't switch it later on in the process, right? Just because I started out by saying, I'm going to put you here because this bin's the least loaded. Well, maybe if that decision turned out to be a mistake, maybe I could change that decision and say, okay, well, you can actually move to your other choice now. That looks better. And Cuckoo hashing, that was developed by Rasmus back there, is one of the ways of doing this. Yeah. All right, so the basic version of the scheme, you get two choices. Can we think of them as being uniformly at random? To insert an item, I'll check both locations, and if one is empty, I'm happy to insert it there. Here, I'm thinking of Cuckoo hashing where there can be at most one thing in each bucket. Okay? So if I try and put something in and I look at its two choices and they're both full, I say, that's a problem because I only want one thing in each bucket. I'm just going to go ahead and put it in one of those buckets and I'll kick out the item that's there, and it's going to have to go to its other choice. And now it's going to go to its other choice, and hopefully that's empty, but if it's not empty, it will have to kick out the other thing that's there, and so on. All right, so what does this look like? Okay, so here I've done this again using sort of a split hash table approach. So it has two choices, but one from each sort of half of the table. And I'm using these arrows to represent, the other choice that it would have to move to if it has to move. So this is where the items are, but maybe they might have to move. Okay? So if something comes in, like an item F, okay? In this case, both the choices are empty, so great, I can put it in one of them, and the other possible place remains free. All right, so here, this item G comes in. So again, you can see now that both of its choices already seem to have an item. So something's going to have to move. Okay. So if I choose to kick out A, what's going to happen after I kick out A? Good. A will kick out E, and then E will get moved to its other location. All right, and again, you can sort of see this is great as long as it works, but there's at least some chance that it might not work, right? So what's going to happen in this situation? What's the problem?
Cycles?
Yeah, I've got sort of a cycle, right? So I'm going to try and stick G in, and I'm going to keep kicking things out, but I'm going to get stuck. I'm going to keep going into a cycle. Or, the way I like to frame this is that, here the problem is I'm trying to put 7 things into 6 slots, right? Which mathematicians will tell you you can't do by what they call the pigeonhole principle and what everyone else calls common sense. You can't stick 7 things into 6 things. All right, so what's the idea here? Again, this multiple choice versus cuckoo hashing. And we've already seen that multiple choice hashing is a really good idea, right? It gives you high memory utilization. It can give you simple lookups, easily coded and parallelized. And cuckoo hashing can expand on this by combining this idea of multiple choices with the ability to move elements, which seems to be potentially very useful both for theoretical applications but also for some practical applications. So in particular, like cuckoo hashing, if we think of, say for instance, every bucket holds only one item, it really is constant lookup time even in the worst case, right? Because I'm just looking at the 2 choices, I'll put what's there, okay? There's high memory utilizations are possible, and the other really nice thing for practice is that these are very simple things to build and design. We have seen that there's already a possibility of failures, right? If the load is too high, you're going to get these cycles. The bad cases, you run into cycles. Alternatively, it might be that just the bad cases when you're inserting, you might think there's a cycle just because you've gone on for so long that you're tired of trying to find out if there's a place to find something. And what you can show is that these bad cases occur with small probability as long as you keep the load sufficiently low. I think I'll have a slide in a few minutes for the 2-choice scheme that I think Rasmus suggested earlier today. That threshold turns out to be 50%, right? Below 50%, it turns out you're fine. That sort of graph that we were getting by, the split table and the random edges, was going to be acyclic, or sort of at most unicyclic with high probability. Now, if you run into a bad situation, in theory at least, you could always just pick new hash functions and try again. That's not necessarily a very useful approach in practice, depending on your application. So we'll talk about some other ways of helping minimize the failure probabilities. The cuckoo hashing is clearly very related to random graphs or random hypergraphs. We'll see in a sec. So So there are various natural representations, right? This is what we were looking at just a second ago, sort of a split table approach, where elements would correspond to essentially random edges, in particular random edges that you give some sort of orientation in a bipartite graph. If you didn't have the split graph approach, then sure enough it would just look like a random graph with orientations on the edges. Or you could think of it as a bipartite random graph between elements and buckets, with the elements being on one side, the buckets on the other, and having the choices coming out from the elements, and having, again, to pick an orientation here corresponds to sort of picking one of the edges. And you can imagine, I guess most easily in this representation, where you have more than two choices for the elements here, and what that would correspond to in these other representations would be hypergraphs instead of graphs. All right, so again, for the basic performance for two choices, as long as your load is less than 50% and you're sticking n elements in, the failure rate is going to be grows like 1 over n, and the maximum time to insert, the maximum number of times you'll have to push things out before you can actually find a slot is growing like logarithmically. And this pretty much falls out of the random graph representation. Perhaps. This one, you can think of the elements and buckets, because here we can just use sort of well-known facts about random graphs, which is that as long as the number of edges is less than half the size of the graph, then with high probability, and you get either acyclic or unicyclic components. And again, cycles themselves aren't a problem, right? If you remember our example, it had a cycle. The cycle wasn't the problem. It was trying to add an edge into the cycle, right? So as long as we have just acyclic or unicyclic components of at most logarithmic size, that means that we'll be able to insert at most logarithmic time and everything will be fine. Then you can start generalizing on this approach, saying, well, maybe I'll do better if I have more than two choices per element, right? And that corresponds to thinking in terms of random hypergraphs instead of graphs. Your edges, right, your items can be placed into more than two, to 3 or 4, however many buckets, which will look like a hyperedge. And you can also think in terms of, well, maybe I'd be better off putting more than one element in a bucket. Might be typical, again, for a cache line. Okay, so again, you can think of, what are the thresholds, what are the possible load thresholds that you can come up with? For bucket size 1, I feel like, whoops, this has got to be this is somehow this is 2 choices is 0.5, and then 3 and 4 and so on. Off by 1. So 2 choices was a load of 0.5, 3 choices gets you already up to 91%, 4 choices gets you to about 97%, and so on. And if you limit yourself to having 2 choices, but you say, oh, I'll have a bigger bucket size, right? You said bucket size 1 was 0.5. Bucket size 2 is already at about 90%. Bucket size 4 is already at about 98% in terms of the load that you can get. So again, you can get very high loads by using these approaches in either setting. Okay. Just a couple of quick notes about these thresholds and where they come from. Most of this comes from viewing the process as a sort of branching tree process. This Cuckoo process is sort of a random hypergraph where we said that each edge corresponds to a key and vertices are a bucket. So you pick some vertex and you start looking at the neighborhood around the bucket. And the distribution, this is just a random graph. It's well known and understood. Locally, it should look like a tree. And then what you do is you sort of analyze this tree and say, well, if I do the sort of natural orientation, I can make sure that everything has a home by looking at some number of levels in the tree. And then usually there are some painful details in fixing up the tree argument, but the nicest way to view it is if you just sort of pretend that everything's a random tree, you can get a lot of good insight. This relates to something that you probably heard come up again with Rasmus's stuff before, or what I was talking about the L-core. Okay. So when we're talking about random graphs or hypergraphs, the L-core is a maximal subgraph where each vertex has degree at least L. Okay. This can be found by peeling, right? The idea is that if I see a vertex around that has degree at most L minus 1, I can just remove it in the corresponding edges. It's clearly not going to be part of the subgraph, so I can just take that out. And once I peel that out, I can keep going. So that peeling process maybe sounds familiar when we were talking about the IBLT data structure from yesterday, where there we were really finding the 2-core that corresponds to finding the 2-core. We kept removing things of degree 1 as much as possible. Okay? So we were left with, or we were hoping that we would get an empty 2-core. It turns out it doesn't matter what order you peel things in. This maximal subgraph is unique, and it doesn't matter what order you peel it in. You know, inductively, you can do an inductive proof to say that you'll always end up, no matter what order you're peeling it, coming up with the right maximal subgraph. So that corresponds to, for cuckoo hashing with buckets of size L minus 1, what you're really asking is, are you getting like an empty L core out or not? Right? So if a bucket can hold L minus 1 keys, that corresponds to our peeling step. Right? We say any bucket that has at most L minus 1 keys that are associated with it, let's just go ahead and shove them into that bucket and then keep going. And we'll see at the end of the day if we can make sure that everything has, again, at most L minus 1 keys in it by this sort of peeling. Okay. So it's clear that cuckoo hashing succeeds when the L core is empty, right? That when we can peel away in this fashion. We can actually succeed beyond that, right? That's the idea of like a cycle, right? A cycle corresponds, in the case where we had in the original random graph setting, where the bucket was a size 1, a cycle is a 2-core, non-empty 2-core, right? Every vertex has degree at least 2, but we can still place things if we have a cycle, right? We can just arbitrarily say, okay, this edge is going in here, and then the rest will follow. And so the same thing happens here. Cuckoo hashing succeeds even when you have an L core, as long as you have a small enough number of edges, you can prove that the remaining core, with high probability, can be successfully matched up. So you can think of the process of assigning things by cuckoo hashing. If you had an offline fashion, it's just doing this sort of peeling argument and then figuring out what to do with the remaining core elements, as long as they're small enough. I was not really going to go through this somewhat painful recursion, which has a bunch of notation in it, but mostly I wanted to show that this really wasn't that bad an argument. It just depends on this sort of tree type argument. So you define the corresponding quantities saying, are things well behaved, some distance, some number of bubbles down in the tree, and you kind of come up with these sort of recursive equations describing what happens as you go down the tree. And those equations will tell you, are you eventually getting into an empty K-core or not? Okay. So some potential practical improvements to cuckoo hashing. Right, you'd really like to keep these failure from happening. Right, having a failure happen would be really bad. Okay, again, technically, in the theoretical sense, you could always rehash everything. But when you tell practical people, oh yeah, if there's a failure, you're just going to take all your keys wherever they are and rehash them. they get very upset with that idea, generally speaking, right? So that will be a slow and painful disruption to whatever it is that they think their system should be doing. All right, so one of the questions is, well, if there's a failure, if something can't be placed. Well, if something can't be placed, you know, is that really so bad? Can't we do something to fix that problem? Okay, so we're doing our cuckoo hashing, we're trying to place things, but it looks like there's cycles or we're not able to find a home for an item. Well, what if we could keep that item off to the side? What if we could keep just one element off to the side, or 8, or logarithmically many, or maybe even it's possible to keep a very small constant fraction off to the side? Is that useful for reducing the failure probability? And this is actually sort of well motivated by, you know, hardware, right? You can think of saying, well, I'm going to have my normal cuckoo hash table, but off to the side I'll have something in hardware which is called a content addressable memory. So it's a fully associative lookup. That is, I can just say, is this object in the content addressable memory? It'll come back in unit time. Now, obviously, if I had a really, really big content addressable memory, I don't need hash tables at all, right? I could just throw everything into the content addressable memory, and when I want to look something up, I just say, okay, find it for me, and it would find it in unit time. The problem is that, you know, the bigger you make these things, or the more expensive they become, and so there tend to be, you know, limits on how big you want to make your CAM. Smaller is better. But certainly you could think of it as holding one item or a small number of items. And it turns out that for instance, for regular cuckoo hashing, and you can do similar things for some of the variants I've talked about. If you have a stash of size S, right, then the failure probability goes to 1 over n to the s. So small stashes can greatly improve the failure probability. Getting it down from 1 over n to 1 over n to whatever power you like in a reasonable way. So now when you do a lookup, you have to look both at the stash and the possible locations. In fact, though, right, usually the stash will be empty. So if you had some sort of flag telling you, hey, the stash is empty, most of the time you probably still wouldn't have to look at it at all. It's really just there as sort of an extra fail-safe device. And you know, the way you can analyze this is, again, just going back to our random graph representation. And now we sort of have to get a bit more careful when we look at these sort of cyclic components. And in particular, we're looking at cyclic components that, you know, are more than unicyclic, right? That it's not just a cycle, but a cycle plus extra edges. Now we have to start bounding the probability of these sorts of things where we have 6 vertices, but, you know, 7 or more edges trying to be placed into them. So we essentially have to go back to random graph theory and bound the probabilities of these sorts of components happening. And using the random graph theory, we can get bounds on what the stash performance tells us. So here's sort of an example, the sort of thing we might see in practice. So we'll have 10,000 elements, a table of size 24,000 with 2 choices per element over, you know, a pretty big number of trials. You can see that like 99.9% of the time, everything works just wonderfully. Right? I don't need a stash. Everything would have worked just fine. Right? On the other hand, you know, that sort of 0.1 or so percent, bad things might happen. Right? That I might get some sort of failure. And on the other hand, once I get to a stash size of just 4, that would be plenty, right? I'd never even need a stash size of 4. The biggest stash size I need would be 3 over this many trials. But if I had a a stash of size 4, I could feel much more secure that I'd never actually see a failure over a very large number of trials.
What was this needed trial? What was this number? Did it mean
What?
how many is this number needed trials? Is how many times it fails?
So 10 to the 7th needed trials. So I needed a stash size of 0 99.9% of the time. So almost always I didn't need a stash. This was the number of times I had one item that would have needed to be stashed. Right? So I actually never actually needed 4 items to be stashed, or would have been overkill. But twice I did need to stash 3 items.
This seems like a significantly greater error correlation than 1
No, remember n is like 10,000. So it's theta of 1 over n. So 0.1% is about 1,000. It's not grossly out of line. If you actually had tables with 1,000,000 elements, I mean that's why I did it with 10,000, was so that you could actually see failures. I mean, if you did it with 1,000,000 elements, the failures would actually be much less rare,
Which hash
or
function
much more
was
rare.
you using the experiment?
I don't remember. Probably just ran, like I just assigned balls random numbers using a random function. That's my typical model of a random hash function. Assign everything a random number using the random number generator. So one question that comes up is when you've got multiple items in a bucket, right? And so I'm putting in a new item, and I find that all of its buckets are full, right? What do I actually kick out, right? If I have, in the case of 2 choices, and sometimes it doesn't matter so much, I'll pick one of them, but then once I pick one, right, it gets kicked out. If it keeps kicking other things out, there's no sort of choice as to what happens, right? When it gets kicked out, there's only one other place it can go, there's only one other place it can go, and so on. But when I have, more than 2 choices to deal with, the question is, what do I actually kick out? Okay. So you could do some sort of breadth-first search, and that's one of the ways that this is analyzed. You say, okay, I'm going to do a breadth-first search through the table, trying to find a place to kick something out. But that can take a significant amount of time and memory, right? It's conceivable even that you might need to look, while on average you might be able to find something quickly. In the worst case, it might take a polynomial number of buckets that you have to look at before you find an empty slot and move things around. So a sort of useful, more practical approach in many situations is random walk cuckoo hashing. When it's time to kick something out, choose it randomly. And that way I don't have to really keep track of the state. Right? I might want to keep track of the last thing I kicked out so I don't go back and forth just because that's wasteful, but I don't even really have to do that. And intuitively, this should work pretty well, right? If there's some fraction of empty things, if I'm doing a random walk through hashing, if I think what's going on is that things are, the neighbors of things are looking random, then maybe there's a probability P of finding an empty bucket at each step. So we'd like that to be true, but that's not actually true, right? There's really no justification for that intuition. Right? Maybe you've got, some little stack component somewhere inside your random graph, and whenever you get in that component, you're really going to have a hard time trying to find an empty spot when you're doing this sort of random walk. So it's a nice intuition, and it experimentally seems like it might be true or close to true, but we don't know how to prove that. Okay, so this is a sort of a good big open question in cuckoo hashing. What's the behavior of random walk cuckoo hashing? How fast will I be able to find an empty spot if I just kick things out randomly when I have to kick things out? And so there are proofs that show now that you can get polylogarithmic bounds on the insertion time. And I forget what the best poly is. I think it's still even a bit bigger than log squared still. But it's still sort of an open question to prove the best possible bounds on random walk cuckoo hashing. And again, I think that's a very practical implementation, so it would be nice if we could actually resolve that problem. I don't think it's resolved yet. All right, so in an attempt to sort of hook up some of the ideas of these two talks, let me talk about a way of getting Bloom filters by way of hash tables. And I think Ian Rasmus was talking about some of these ideas this morning. So recall that one way that you could get a Bloom filter in the static setting is to use perfect hashing. Okay. That was this picture here, right? You sort of hash things and keep fingerprints using our perfect hash function, and we use that as our Bloom filter. Now, multiple choice hashing and cuckoo hashing, you can think of as they're giving us sort of near perfect hash tables, right? They're not 100% full, right? But we saw that like cuckoo hashing could easily get things with a small number of choices to be 97% full, 98% full. That's pretty close to full, right? So it's a near perfect hash table. So could we use that in this sort of fingerprint type approach to get a Bloom filter type structure? Okay, that might be better than our other Bloom filter type structures. Okay. And I had worked on this some number of years ago using d-left hash functions. If you try and say the maximum load for a bucket equals 1 using d-left hash functions, problems sort of occur. It's very hard. You're going to get a good number of spillovers. But again, this idea saying, well, if I could, as we saw in the tables before, if I say, well, I could put an average of 6 things in a bucket and be almost assured that I'll never have more than 8 things in a bucket, right? Then I can get 75% space usage by using these buckets. But now notice there is a difference with the perfect hashing approach in that I'm not going to have just one fingerprint in a bucket, right? I'll have 6 or 8 or however many fingerprints within a bucket. Right? If my bucket can hold 8 things, I might have 8 different fingerprints in a bucket, which means that my false positive probability will go up by a corresponding factor of 8, right? If I see an item, I'll figure out what bucket it's in, right? And then I'll have to say, oh, if it matches any of these fingerprints, that's a problem. So in fact, it's sort of twofold, right? I'm going to have to worry about how many fingerprints I have in the bucket, and I may also have to worry about how many buckets I'm actually looking at, right? If I have 4 choices of buckets, then I'm going to have 4 buckets, each with 8 possible fingerprints. Matching any of those fingerprints would cause a problem. So I'm going to have longer fingerprints to make up for it. But maybe because I'm getting this very good space utilization, that will end up being worth it. Okay. And in some settings it is. But now, let's go look at sort of a modern update of this. There's some recent work I've been doing with some people on cuckoo filters, right? So let's use a cuckoo hash table to attain the near perfect hash table. Again, we'll store fingerprints. And one of the things we'll see here is this going to support, if we do things right, we can support insertion and deletion of keys, right? So while Bloom filters could just handle insertions, here we can also handle deletions and still come up with something very space efficient. All right, so let's think of a cuckoo hash table where I'm going to have 2 traces per key and 4 fingerprints possible per bucket. Okay. All right, so buckets will fill up, and now let's suppose we get to this place where I'm inserting a new key into the system. Okay. I I've got my two choices, I've got my buckets that can hold 4. What if they're all full and now I have to move something? Okay. So now I say, normally when I move something, right, I say, okay, I've got my object. I'll figure out its other hash location, and then I'll move it to that other location. Right? So I'd have to take my key, take my stored object, hash it, and move it to its other location. But now I don't have the key anymore. Right? This is a Bloom filter type data structure. All I have is the fingerprint. I don't have the key. So how am I going to know where to move? Where to move the key? What's its other choice? I don't have the key anymore. How can I possibly move it? Okay. Do people see what the problem is? I no longer have the right information to do a move anymore because I'm not keeping the keys. All right, so the idea that someone came up with is we're going to do what's called partial key cuckoo hashing. And that my two values, my two choices, one will be a hash of the key, and the other will be the hash of that key exclusive ORed with a hash not of the key itself, where it's going to depend instead on the fingerprint. Okay, so the second hash function is going to depend on the first hash function along with the fingerprint. And notice that what this means is that I can compute H1 from H2 in the fingerprint, or vice versa. Right, so given the fingerprint and its current hash location, I can figure out the other hash location and always store the fingerprint there. Okay. Now, the problem with this is that now I'm not getting two full random choices anymore. Right? If my fingerprint is short enough, right? The whole idea is I want to keep short fingerprints because I want to keep this small. Right? It may be that if my fingerprint is sufficiently small, right, that I can't possibly get all possible pairs of locations. If I use like an 8-bit fingerprint, right? If I use just an 8-bit fingerprint, there's only going to be 256 possible hash values here, where I might have a table that's 65,000 big, say, or bigger. So how do I know that this is going to work? Will this still work? Okay. And this is sort of a funny result that we have, which is that it works great in practice, right? And it fails miserably in theory. So in theory, it clearly doesn't work, but it still actually works. Okay. So the idea is that, and I think I've left this as, might have left this as one of the exercises. What the theory will tell you is that you need logarithmic sized fingerprints. Okay. But the constant factor in front of the log depends on your bucket size. Okay, it turns out the constant factor you need in front of the log is going to be something like twice the bucket size. So remember here we were talking about a bucket size of 4. Okay. So twice the bucket size of 4 gives us a constant factor of 1/8. Okay. So what the theory tells us is that, yeah, you need a logarithmic sized fingerprint, but that logarithmic sized fingerprint is like 1/8 of log n. 1/8 of log n is usually constant. The constant factors actually do matter. Okay. So in practice, this works fine as long as we're only dealing with size n of a few billion, so that log n is a reasonable number. Then 1/8 of log n is small enough that you don't have to worry. So it's one of these interesting, funny things that you can see sometimes when you try and work in practice, where the theory is sort of telling you something bad, but it actually still works okay, and there's a good reason for it. Again, another sort of open problem here is, we have sort of a very limited understanding of sort of the performance of partial key cuckoo hashing. It would be nice to get more.
Can you just specify then what you mean by that you need that big fingerprint? Does it mean
if you have perfectly random hash functions, you would fail because there's going to be, essentially what you can show is that there's going to be, remember, you're going, think of having 2 buckets, each of, that can hold 4 things. So what you can show is that you'll end up getting 9 things that want to go in exactly that pair of buckets with non-negligible probability. So if your fingerprints are too small, there's going to be some pair of buckets that's going to have 9 things that want to go into them, even though it can only hold 8. Is the problem? Okay. So there's some other fun technical things that you can do, right? So when we're talking about trying to minimize the space, every bit counts. So when we have buckets of size 4, right, and we're storing 4 fingerprints in a bucket, we can store them in any order we like, right? It doesn't matter what order they're stored into the buckets. It just matters that we know what fingerprints there are. So let's sort the fingerprints and take the 4 most significant bits for each of the fingerprints. So that gives us 16 possible bits. Okay. But because of the sorted order, there are fewer than 2 to the 16th possibilities for those 16 bits. There's only, turns out, 3876 possible outcomes, which is less than 2 to the 12th. So by doing a lookup table on those 16 bits, you can use 12 bits to represent these 16. So save essentially 1 bit per entry. Okay. You have more time because now you have to do these sort of lookup operations in order to figure out what those bits were. But if you're interested in space saving, that turns out to be important. Okay. All right, so if we compare Cuckoo filters versus other sorts of filters, versus sort of a standard Bloom filter, you can see that for big false positive probabilities, sure, you're probably better using a Bloom filter. But once you get to false positive probabilities of less than 3%, it says, it's like closely around the 1%, right? Then the Cuckoo filter is going to do better in terms of space. And again, the blue line here represents the standard Cuckoo filter, and this green line represents what happens if you save that bit per entry that I just talked about using the sorting. Now you may look and you say, hey, it doesn't look like you're that much better than a Bloom filter, except remember that the Cuckoo filter can handle insertions and deletions. So besides being space competitive and actually space better for very practical false positive rates, you also get the power to delete, which you couldn't do with a standard Bloom filter. All right, so I think we're getting near the end, so I'll conclude. So in some sense, both of my talks have been about the power of using multiple hash functions, the power of having more choices. In this talk, really the power of 2 or more choices, that a little choice goes a long way in terms of load balancing in particular. And I think what we're seeing in practice is more and more people are finding uses for this sort of multiple choice and Cuckoo hashing techniques. There's certainly still lots of theoretical questions, particularly on Cuckoo hashing, left to solve. And so there's still research to be done, I think, that can have an actual impact on how people design and use these things. Before I just end, again, there'll be some exercises that I think will be handed out that you can look at and do. One of them is to come up with sort of the corresponding differential equations for the D left scheme. Sort of even harder thing then is to show that this would lead to the sort of Fibonacci exponential decrease. And one is this sort of the question you asked, showing that partial key Cuckoo hashing can fail. Essentially by showing that you can have 2b plus 1 keys, again trying to map into the same 2 buckets, each holding b. And there are a whole bunch of, clearly that I don't expect you to solve over the course of the summer school, but interesting open questions related to cuckoo hashing, analysis of random walk cuckoo hashing, partial key cuckoo hashing, double hashing with cuckoo hashing, do the same thresholds still hold? Double hashing and peeling, again, do the same thresholds hold? There's been some work that I've done with some students on the latter two problems, but we're still far from a complete understanding. Needs to be some interesting open questions, I think. So I'll take more questions, but that's it.
So with random walk cuckoo hashing, does it make sense to, so if the walk gets too long, to restart it? That's good in practice or in theory?
I think it may be a reasonable, useful thing to do in practice. I don't know of any theory that tell you that that's better. But it could be. Right. So, the analysis, the polylogarithmic bounds come from examining the random graph structure, and sort of saying that after some number of steps of the random walk, you're likely to be close to an empty node, right? That it mixes enough that you're likely to be close to an empty node. And then the question is, then you get lucky and find the empty node. And if you don't, then it sort of essentially does a restart. The analysis does a restart of its own and says, okay, now I don't know where you are, but it's like you're starting over from scratch again. So after some number of steps, I expect you to be close to an empty node, and then do you find it? And sort of repeated process. So in some sense, the analysis is, it's not actually doing a restart, but the analysis is restarting, and it may be that maybe it's better to restart somewhere along the way or back at the beginning.